Hi, everyone. Welcome to week 6 of the summer term. Professor Rios here. Hope you're doing well. This week it is a lighter week. It's coastal processes and landforms and glacial landforms and landscapes. So it is a significantly less stressful week in terms of material because it is also simultaneously the final exam week. So please bear that in mind. There are some good videos that you can watch, especially one called Beach, a River of Sand, which explains a lot of the material in this particular lesson. And this particular week, you should definitely watch not only this video, which I guess you wouldn't be hearing this if you're not watching it, but you should also look at the lesson slides carefully because one of the questions in the homework, which is worth quite a bit, is based on Google Earth and material from this lesson packet. So, having said all that, let's get going with the first part. Glacial landforms and landscapes. This is a glacier at the end of the southern tip of South America in Argentina. So, glacial landscapes are becoming lesser and lesser available or visible due to climate change. Lots of glaciers, especially ones on mountains, are being lost for probably a very, very long time. Continental ice sheets like Greenland and Antarctica still remain. So these are the lesson objectives. And when you look at an image like this is great because you can see the terminus of the lake of the glacier where it ends. And notice because of all the material that's been carried, all this gray stuff, it's deposited as it melts, and so you have a braided stream, usually associated with the end of a glacier. Notice as you go north or up, rather, it goes from gray to white. So this is the only area of the glacier that's actively growing, whereas the rest of the glacier is slowly receding and melting. So that's one of the consequences of climate change. Here you see all these little tributary glaciers that are sort of feeding it. Again, look at this image here. Look how much material and rock and soil and sand and pebbles and boulders ice can carry, and it can absolutely shape a landscape quite significantly and quite obviously. So these are some of the key terms. And why study glaciers? Well, our area of the world, New York State, the Hudson Valley, is an area that is shaped by landscapes. All the little lakes you see around New York, Harriman State Park, the Catskills, Orange County, Putnam County, Westchester County, they're basically all carved out by ice. The way the Hudson River looks through places like West Point and Newburgh and up the Hudson Valley towards Poughkeepsie, it is all as a function of glaciers. The Pleistocene Epoch. So it's a time that started about 1.5 million to 2.5 million years ago. It ended about 10,000 years ago, which is the technical term, the technical time when the glacial period ended, and is an area or a time rather defined by glaciation. This is the areas of the United States and Canada that have been covered at one point or another by glaciers. Notice New York State is. Uh, Glacial periods mean lower sea level, and warm periods mean higher sea level. So here you see the modern New York, New Jersey shoreline, but this line here represents what the shoreline would have been like around 21,000 years ago when it was the height of glaciation in the northern hemisphere. Glacial ice today is limited and minimal, so you find it in places like Alaska in mountains. You find a few in the United States in higher terrain like Montana, Idaho, California, Oregon, and Washington. But by and large, glacial landscapes in the United States are being lost. So mountain glaciers are a function. That's what this little F here means. They're a function of latitude and altitude. The lower in latitude, the higher you have to go to find a glacier. And the higher in latitude, the lower you have to go. So if you're in Alaska, you can find a glacier at sea level. But if you're at the equator, you have to go really, really, really high, like at the top of the Andes Mountains, for example, in order to find one. And ice sheets are a function of latitude, so you only find ice sheets as of now at very, very high latitude. So, for example, the South Pole and Greenland, which sits mostly above 65 degrees north latitude. And this ice can be very, very, very thick. Glacial formation. Well, glacial formation takes snow and compresses it. And once that compression happens, all the air is lost and the snow goes from fluffy to granular to ice. You're literally expelling all the air from in between each little bit of snow. And that's how glacial ice begins to form. Glacial balance or mass balance is a fine equilibrium game where you have a zone where there's melting and evaporation and you're losing ice to an area where you're actually accumulating it. Regardless, ice is moving downhill. And if this line, called the firn, FIRN, is beyond the glacier, then the glacier is going to grow. As you can see in this particular image here, this means that all this is being lost over time. And that's the definition of glacial mass balance. It can be positive and negative. In this particular case, it's negative. You are losing mass, even though you still have a zone of accumulation and a zone of ablation. Ice basically moves like silly putty, if you want to think of it that way. And there are two ways of thinking of the movement. It's either basal slippage, which is what happens at the very, very bottom of the glacier where it meets the rock. And then plastic deformation is what happens when faster moving top ice moves slower than the ice that is in contact with the ground. And it literally deforms over time. Here's some examples of the movement. Ice can pick up a lot of material and basically break it up and carry it with it very, very, very far. These are some of the effects. So you can have material be literally picked up and moved. Water freezes, it goes into cracks, it expands, and then it literally gets plucked out. Continental ice sheets are only two, Greenland and Antarctica. And that erosion work as a function of continental ice sheets can do quite a bit of work. Namely, places like the New York Finger Lakes, if you've ever been up there. Glacial deposition lakes is one such example, but other ones are called moraines. And moraines are basically bits of material that have been collected over time. So as the ice moves, it leaves behind, it's sort of like when you push your finger down the tray of a blackboard and your finger leaves behind a little bit of dust collection. That's what a moraine is. The terminal moraine signifies the furthest the glacier has moved over time. You can have recessional moraines, you can have ground moraines, and you can have moraines that happen in between glacials. So here's the idea. The ice moved in this direction. It left behind a mound. As the ice began to retreat, it left behind the same mound And when the ice melted completely, it left behind the mound still, even though this area here is now ice free. Till is basically all the big bits of rock and boulders that are carried by the ice itself. The outwash is what is carried by the melted water. So it tends to be more layered and stratified than till. Here's, for example, places in the United States that have been covered by ice. Here's an example of a mountain glacier in the United States, the mountain called Mount Rainier, which is basically south of the Seattle area. Mountain glaciers, again, function pretty much like rivers, but the only difference is that mountain glaciers are much smaller. They move pretty quick, but they're more susceptible to big changes in climate. So you currently find them in the European Alps and in places like northern Canada. And here's an example of a classic ice-carved valley. It is called a U-shaped valley because the ice at one point occupied this entire landscape here. And this is a place in Switzerland which is very distinctive U shape, if you can sort of follow it right here. Here's the U. Whereas a non-glacial valley, for example, this valley is a V-shaped valley, which means water is the only component doing the erosion. Had this entire valley been occupied by ice, it would have looked like that. Instead, it looks like this. Okay, so there's the idea of moraines, terminal moraines, lateral moraines, recessional moraines. Here's an image, the red arrow showing you where the furthest extent of the ice was. So there is your terminal moraine. In this image here, which is fantastic, this is a place in Canada. There you see the moraine on the lateral side, and for perspective, I don't know if it's easy to see, but this is a road, and these little dots are cars. Therefore, these lateral moraines are big. They're like small mountains that have been basically deposited over a very, very long period of time. Notice how dirty the water looks. That means that water is filled with sediment that has been laid there by the water. That is the outwash in the outwash plain. Notice how the ice goes from brown to gray, and by the time you get way up here where it is much colder, you have white. So if you go back to that glacial mass balance image, you see that the firn line is probably somewhere up here. So this glacier is slowly disappearing. And here's the idea of drift. We've already talked about outwash, which would be this, laid down by the water. And the other would be unsorted, which is basically what happens at the end of a mall parking lot when the plow lays all those big snow piles. When the snow is gone, you're left with bits of asphalt and Coke cans and cigarette butts, right? It's all unsorted. It was picked up by the plow and moved in that particular direction. So that's the idea of drift. Drift is either sorted or stratified by the water, or it is unsorted and left behind by the ice itself. Here's an example of sorted. Notice how layered it looks. Here's an example of unsorted material. Yosemite Valley in California is a really, really good example of a U-shaped valley. And this one in Alaska is a really good example of a a braided stream, because all this, there's so much material that was laid down by the water that the water has to find its way through all these thick gravel bars. This is called a glacial erratic. Ice is very, very powerful and can leave weird looking features in places that shouldn't have them. So that's the first lesson. Um, we're going to be moving on to the last one, which is the coastal processes and landforms. Again, be sure to review the material on the slides. And so, with that being said, let's move on. So, the beach. Everybody loves the beach, right? So, these are the objectives. Like, what is a beach? What does that mean? Where does sand come from? All that good stuff. So, the coastal zone is both high energy and dynamic, meaning it's changing all the time. And here's an example of that power. This is the same area before and after a major tropical cyclone. And beaches change, and they change quite a bit. And they change quite a bit because there's so much energy being spent on the interface between the water and land. So, energy, wave energy is a function of the wind, of course. Factors that influence the way a coastal area looks would be obviously the energy of the water, the sediment, sea level, and of course, you have to take into account the people factor. So, a beach is a depositional landform, which is a response to whatever available sediment is there: sand, pebbles, coral, or a combination of all those things. The beach, we only see but a part of it, right? You only think of the beach as what you put your umbrella into. But the beach is low tide, high tide, where the waves begin to break and where the surf makes changes to what you have in the form of sand deposition. So, depending on whether it's low and high tide, there is a significant and season, of course. Um, the beaches will change with the seasons depending on how much energy is available. Think about winter versus summer. Summer storms are less energy, they have less energy associated with them, and whereas winter storms, think about a big nor'easter or a hurricane, they tend to have a lot more energy. They're more dynamic events, and as a result, they change the profile of the beach much more dramatically. Wave energy is basically a function of waves, and waves are in response to wind. So now, wave energy is a function of the height square of the wave. So imagine a 1 foot wave. You can stand on the beach and be able to handle a 1 foot wave. How about a 2 foot wave? Yeah, you can still do that. That basically goes up to about your thigh. But once you go from a 2 foot wave to a 4 foot wave, think about it. 2 squared is 4, but 4 squared is 16. And if you go from 4 to 8, 8 squared is 64. So energy is increasing by an exponential rate. And while you might be able to handle a 1 or 2 foot wave, maybe even a 4 foot wave, you won't be able to handle an 8 foot wave. I guarantee you that. If you're just simply standing on, like, if you're standing like here and an 8 foot wave comes, you're going to be tossed around like a little rag doll. So that's a function of energy. And the energy is a function of the height of the wave squared. Okay. Wind waves are generated by wind, and that is a function of wind velocity, duration, and basically the depth and the fetch. And fetch is the distance of water over which the wind blows. So if the wind is blowing over Delaware Bay, it can only blow over this small area. But if the wind is blowing over the Atlantic Ocean, it can blow over a much, much, much longer area. And as a result, waves can be bigger. Okay? So here you have a narrower fetch, smaller waves, longer fetch, larger waves. The idea of waves is that the critical depth is about one half of the wavelength. So basically, as waves begin to approach the coast, um, they begin to feel the bottom of the ocean, and that energy has to be expressed upward, and the wave begins to grow. In a tsunami, something slightly different is not a function of wind, but it's a function of displacement of water, and that water then has to go somewhere. So think about the idea of dropping a bowling ball into a kiddie pool, right? That water is going to be pushed entirely in all directions, and what you get is sort of a sloshing motion and a spill of that water. Here's an example of what tsunamis can do. Again, once the water recedes, it has to come back. And here is that video that I highly recommend. It is 19, even though it was made in 1965, the documentary is still very much worthwhile. It's about 20 minutes. So, but I really, really highly recommend it because it is really well done. And it explains a lot of the concepts having to do with this particular lesson. Longshore current, that's a pretty big, important aspect that's discussed in that movie. But the idea of longshore is that the waves approach at an angle, and you see that here. And as they do, they induce a current. So, for example, let's say you go to this beach and you set up your towel here, nice and dry. You put your umbrella and you decide to go out in the water. And then you just decide you're going to basically bob and float. Over time, you're simply going to do this. You're sort of going to wind your way down the shore. And if you do nothing, you will suddenly find yourself here. And you're going to be wondering, wait, I used to be across from my umbrella. Now my umbrella is all the way out here, even though you started here. So that's the longshore current. So this implies, if you look at this video, it's called beach, a river of sand, and the sand is being transported in this river. One bank of the river is this, the other bank is where the waves begin to break. So the river is basically this. And so notice, and this is important for that homework question, here you have the waves approaching at an angle, and the implied current goes in this direction. Okay, that's the longshore current. So the idea of littoral drift is a function of beach and longshore drift moving along the longshore current. And sand gets sort of, it goes forward, it comes back as the waves break back and forth, back and forth. But in the end, sand is being transported in this direction. And you get to see things like spits form and other sand depositional landforms happen as a result of running out of land. So when the longshore current slows down, whatever is being transported in it gets deposited. And so here's the idea of sediment and transport and deposition. When you have things like this where you have headlands, the energy is concentrated in here, and then the sand gets deposited here. Now, this is the important part for the homework. This is not in your textbook, but you are responsible for it, so pay attention. These are the four engineering structures that are basically established along many shores. One is called a groin, a jetty, a seawall, and a breakwater. A groin is simply just one of these. A jetty is two side-by-side groins, and they basically enable the movement back and forth between the ocean and an inland water body, like a sound. Okay, so that is a jetty, two side-by-side groins, a groin, which is an individual one, and then you have a seawall and a breakwater. So here's an example of groins, and this happens to be in West Hampton Beach in New York. And here's an example of a groin in the town of Monmouth Beach, New Jersey. Okay? Now, here's an example again in North Carolina. And here's an example at another location which I can't remember. But regardless, you can tell the direction of the longshore current because the majority of the sand will be accumulated at the point where the water is moving fastest. So basically what happens is, in this case, notice there's more sand on this side, on that side, on that side. So here the longshore current's moving like this. Here's another example, jetties. Notice how there are two side-by-side groins. Notice how the beach is wider here than it is here. So what happens is the longshore current comes down, it slows down as a result of this. It deposits the sand, making the beach wider, but then it picks up speed again and it does severe erosion on this side. And so the beach here is narrower than it is on this side. You can see the same effect in these images as well. So notice how the beach is wider here than it is here, wider here than it is here, and so on. And here's an example again. This is the Indian River Inlet in Delaware. Notice how the beach is less wide here, and it is much wider here. The longshore current is moving from the bottom of the image up. It slows down when it hits this, deposits sand, makes the beach grow. Then the water picks up speed again, eroding this, making the beach less wide. Here's the idea of a breakwater. A breakwater is basically there to make the waves break, therefore making one side of it much lighter in terms of turbulence, and therefore a place where you can anchor small boats. And of course, a seawall. All the energy is spent on the seawall, therefore it protects the land on the other side. But it ruins the beach. There is no beach here, basically. So that's what I have for you. Again, not a lot of material. Again, be cognizant of the fact that this lesson is less busy as a function of the fact that this week is also the final exam week. So with that being said, I wish you the best of luck. If you have any questions, please let me know. Otherwise, I hope you are doing well. And if you have any questions, send them my way. Bye.